So it's a pleasure to, for the last talk before our break, to have Raul Tempone here. He's going to talk to us today about uncertainty quantification with multi-level and multi-index methods.
Thank you, Clayton, and thank you very much to the organizers for inviting me here. It has been a great meeting so far, and I hope not to change that trend with the talk. Now, I'm going to do an overview talk, so you will forgive me if I do not go into many details at some point, but I hope I will give you the idea and the flavor of the things that we talk about, and hopefully, if you have more questions, we can just discuss in the break and elsewhere. Okay? Some of my collaborators are knowledge here today. So Joachim, for example, Lorenzo, who is sitting over there, Søren, and Fabio, who is over there as well. So, without further ado, let's go into this. Given the audience, I included, because I didn't know how much I would have to talk about different things that at this point of the meeting look a little bit repetitive, but this is just to set up a notation. So the point that we will be doing again will be sparse approximation combined with different sampling techniques in different contexts. And first, let us recall Monte Carlo via a quick motivational example, which in this case is a differential equation. It's a linear elliptic PDE, and we want to compute a functional S, actually the expected value of S, out of the solution. Now, this is just to explain at the beginning what we can get with Monte Carlo, but later we will go into response functions. Okay, I know the workshop is about response functions. We will come to that in due time, so don't worry, don't get nervous. Now, seldom have we the ability to compute the exact solution U, and we have to resort to numerical methods. So we will think that here, instead of computing samples of the exact U in Monte Carlo, we use an approximate realization UH out of a numerical method that we choose, right? And this produces a bias and a statistical error. This was discussed, fortunately, in the first talk given by Catherine, who is over there, yeah? So, and she essentially introduced this notion of minimizing the work subject to a constraint of accuracy, which in this case is denoted here by tolerance. So we want to make these two errors in probability less than tolerance. For each of them we have a bound, we minimize the bound, and we use the bound as a constraint, and we minimize the total work, which is the product of the samples times the average cost per sample, right? And this is expressed in terms of the discretization parameter of this PDE in this case. What do we get as a result? We get that, well, the optimal work is essentially the product of the samples that you need to make the sampling error, the statistical error less than toll, times the work that you need to make the bias for each of the samples on average less than toll. Okay, and this relates to the quality of your numerical method, which is given here by W, right? The convergence rate here, and the gamma that relates to the dimensionality of the space where you solve, and gamma is related to the quality of the linear solver that could range, of course, in this case between 1 and 3. Okay, so that's what we can get if we just take a finite element code and we sample at a given mesh size, so we get to the bias level. What else can we do? Well, let's introduce some notation. Okay, so what do we do in this case? We consider that we have one problem where we have different parameters to play with in our discretization. We call these HIs. Each of them are refined from an initial mesh size, say up to alpha I refinements, and think of this beta as just 2, say, for example, just to simplify the life. And therefore, if you fix your numerical discretization, right, and you fix the number of refinements that you need to do in each of these parameters, your numerical solution is uniquely defined. This is the tacit assumption that we always make, right? Now, remember, we were trying to compute an approximation of S, and this approximation in this context will be S alpha, where alpha relates to this multi-index that we here depict, right? Each of the components are alpha I, and they connect to discretization by this. All right? So one discretization could be X, the other could be time, but it could be a million other things, like, for example, number of particles in a stochastic particle systems and other things as well. Okay? So, well, you may think that that was a little bit constraining in terms of the structure, but it is not really. We can treat several problems. Now let's look at the first use of this notation, which is multi-level Monte Carlo. In this case, we think that we take all discretization somehow in all directions, growing at the same rate, essentially, given by this level, little l of discretization. So essentially, if we have a PDE like we described first, it would be x, y, z, for example, right? We would be refining delta x and delta y and delta z in the same fashion, right? We start from a mesh and then we divide each of the directions by 2 and so forth. Now what we create to describe the multi-level Monte Carlo is the so-called consecutive differences, right? These are the delta tildes s here that are differences between numerical approximations. The exact solution does not appear in this construction, of course. This is just based on discretization, so this will be the coarsest level, and for the others we take differences between consecutive approximations, right? So we take one refinement minus no refinements at all, and so forth. Now this allows us to decompose the exact expectation that we wanted in terms of an error, right? There will be a bias error, right, between this guy and this guy, precisely like we had in Monte Carlo, and this actually is represented exactly in terms of these differences. There is no loss between left and right here. Now, if you do that, you sample a la Monte Carlo each of these terms, you get to multi-level Monte Carlo, and provided that these delta tildes converge sufficiently fast with respect to the work that you have to invest in order to sample them, you can have improvements with respect to the complexity of Monte Carlo. All right? And this let us discuss it in terms of the assumptions then. So the assumptions that we need in this context are related to the bias convergence, right? This will be the approximation of the expectation of S by the expectation of SL, or this is natural to be assumed. Here is it related essentially to the discretization of the PDE only. Variance also relates to the discretization of the PDE, but you may have a rate that may or may not be 2W in this case. So we have to be, problem dependent when we estimate W and X. And finally, the work is the same thing as we had before, but rewritten in terms of beta. In this case, remember, we have h to the minus d gamma. Well, this is the same thing, but written in terms of beta. So what is the conclusion then after you make these assumptions on the multi-level behavior, right? Well, the conclusion is that you have three regimes, namely if the strong convergence goes faster than the exponent that comes from the work, that was d gamma, you get the old optimal rate that is essentially O of tau 2 minus 2. And I say optimal because this is a rate of growth in the work that corresponds to being able to sample exactly the realizations without having to pay more than 0.01 cost per realization, right? So it works as if you have access to the exact solution of the PDE, at the cost 0.01, okay? Now, there are other cases, namely the limit case when S is d gamma, and when S is strictly less than d gamma, you still have an advantage with respect to Monte Carlo, of course, provided that I'm here making no comments on the constants, right? But as you will see in the numerical results, they do not make much difference. The difference is in exponents. So you get an improvement from the rate of strong convergence with respect to Monte Carlo, okay? So there are many questions related to multi-level Monte Carlo. Some of them were touched through the workshop, right? I mean, one of them is how to choose the mesh hierarchy HL, right? We said that we were taking essentially refinements that were geometric. Essentially, we were dividing, say, by 2, by 4, 8, and so forth. Why is this optimal? Not clear. In fact, it is not, okay? So you can actually show that you can actually solve the optimality problem and find the HLs depending on the different input parameters, which are the constants and the exponents. Another tricky thing is here the estimation of the variances that appear in multi-level Monte Carlo. Namely, if you want to, for example, here, let's see, where do I have this? Here. If you want to, for example, estimate correctly the work of multi-level Monte Carlo, you have to invest essentially the right number of samples per level. But in order to find those, you need to solve an optimization problem whose input are these variances, which are not given a priori to you. Okay? So you need to efficiently learn somehow these variances as you solve the problem. Otherwise, you may deteriorate naturally the complexity of your solution. So that's another question that is important. And of course, can we do better specifically for d larger than 1? And this relates to the multi-index technology. Essentially, if you see these inequalities here, they are all indexed in D, right? They depend on D. And the larger that D becomes, right, the more likely you fall into this case if you use the same sort of discretization in the PDE. So what can you do? If there's smoothness available, can you actually remove this D from this picture, right? This will make further problems fall into this category, which is what you really want. And of course, this is a limitation that comes from Monte Carlo sampling, right? If you change the sampling, because you again have further assumptions on regularity, for example, you can get either rates that correspond to quasi-Monte Carlo, or even better, for example, sparse grids with optimal rates in case of, for example, holomorphic type of dependence like Kirchhoff was presenting the other day. So, okay, so these questions were addressed here, and also we studied the time adaptivity for MultiLevel Monte Carlo for itoSDEs in different contexts, and the papers really develop a theory for the convergence rate of a resulting adaptive algorithm, right? So this is for the adaptive. Okay, so variance reduction, as I was sort of trying to give you by cartoon depictions, you are trying to pass essentially by control variance techniques, essentially realizations from a costly mesh onto a less costly mesh. All right, this is the idea. But this essentially says that this guy somehow has to be approximating this guy in a fine way, and the cost to evaluate realizations in this mesh should be smaller than the cost of evaluating the solution there. Now, these are not the only meshes that you can think have this property. For example, these other two have the same property, right? The dependence on the work is slightly different because here I just de-refine only one direction and here in the other. But in principle now you can think of, from the control variance perspective, of using these three guys actually to reduce the variance of this one, okay? And this is essentially what is behind this multi-index Monte Carlo, right? You now use difference operators that use de-refinements in just one direction at a time, right? Then you tensorize them, and of course you see now that I changed the notation slightly. I don't use the tilde. I mean, this is delta now acting on these different directions, not as in MultiLevel Monte Carlo, where you acted as long as along one only. And the multi-index Monte Carlo, then once you write this in terms of the alpha decomposition, looks deceivingly close to the multi-level, except from the fact that, of course, you have to remember these alphas are multi-indices, and these deltas are mixed differences, not just single difference, right? So why is this going to work sometimes? Well, this is going to work because if you have the right smoothness, somehow, this mixed difference here will converge in L2 and in the mean way faster than those that are coming from Monte Carlo, from multi-level Monte Carlo. This is the main change. So even though this set now looks larger, and it is larger because you're summing over a multi-index, right? But you're summing here potentially it's smaller. So, and again, before in multi-level you were just summing along levels, right? So you just have the task of finding the largest level, so you could control the bias. But now you have, a subset of a lattice, right? A subset of n to the d, and then you have to somehow even try to understand what is the optimal shape of this I set. Yeah? And this is an optimization that is discrete. Okay, so mixed differences. This doesn't need to be discussed too much. Now the same here. We always try to control in probability the error between the exact solution that we are seeking and the sample-based answer that we're going to give, which is A in this case, right? So if you have a central limit type of approximation, you can get rid of this horrible constraint in probability and approximate it by a constraint of the variance, which is much easier to handle it algebraically. And then, of course, you again solve the problem of the optimal number of samples, which again requires that you know these variances in a neat way, and get to the optimal work on multi-index. And again, this is key now to try to understand what is the best way to choose this set I, okay? So once you substitute the optimal number of samples in terms of I, you get to this expression. This doesn't depend on I anymore. We assume that this is not really important. It's the cost of one sample per index, and the whole thing connects to this now. So now you have to find I in some optimal way, say. So the right insight here is to understand that that work essentially with the bias constraint can be recast as in a knapsack type of optimization problem, and the way to solve that is to threshold the corresponding profits. Okay, the corresponding profits are quotients between the error contribution and the work contribution, work coming from this contribution. And once you do that, well, you understand which are the shapes, the optimal shapes of this index, in a set of indices that you have to use. Okay, and that's how it goes. Now, you can say, well, now what do we do? Well, we need the corresponding sort of assumptions that we have in MultiLevel Monte Carlo, right? In MultiLevel Monte Carlo, we have assumptions on the convergence of the weak error, and in L2, remember these things. Now we need to have something related to multi-index, okay? And in that case, we will have to make assumptions on the convergence of the expected value of the mixed differences and the variance of the mixed differences, and of course on the work, okay? For each problem, you will have to identify how this convergence happens, what is the type, and from there you will get to the optimal discretization sets, and from there you get to the complexity result, okay? And I'm going to discuss just one type of assumptions that is fairly common, but it's not the general case. And again, it looks really close to the multi-level again, but you get, instead of a single type of convergence here with respect to a single parameter, you get the product of the convergences in the different directions, okay? And this is because you're taking a difference of a difference of a difference of a difference. So you get one of these convergence rates from the first differences, and then you compose it again and compose it again. You get, provided the right regularity, you get these products. Same with the variance, and for the work, it's really not assumption, it's just by construction. So if you have this thing, right, then you can make the quotient between E and the square root of VW, and you get to optimal discretization sets, alkaligaf, that are sort of weighted or anisotropic total degree. Okay, this is how these things look like. And you say, okay, how difficult is to show these things in practice? Okay, it may or may not be. There is one discussion of a nice structure on the work that we have with Søren here and Fabio. That is the assumption of multilinearity. So essentially, if your solution actually is a multilinear form on different operators, and these operators are approximated by, say, these AI operators here, and for each of these AIs, you have this component-wise approximability. That is, for example, for the finite element type of approximation, you have this kind of convergence, and then for the say other type of sampling, that you have another type of direction that is acting in this way. Well, if this multilinear map was continuous, you inherit the product directly of these convergences for the approximation of the for the control of the mixed difference. Okay, and this can be used in multi-index context in a very natural way. You may say, okay, do you really need to assume that your problem was linear or multilinear in this context? Well, one example shows that actually this structure is more common than you think. Suppose that you were computing the expected value of Q of UI, like the example that I showed at the beginning, right? This is an integral of this quantity of interest. Now the integral operator with respect to this measure and the solution operator that gives you this Q are both acting bilinearly on the solution, right? The final solution is a real number, and these two here enter in a bilinear way. And now if you approximate this by a quadrature that could be, for example, based on Monte Carlo, and this one by a finite element approximation, you only have to concentrate on showing that the quadrature has the right type convergence and the finite element has the right type convergence, instead of having to deal with the things at the same time. Okay? So yeah, so let's see. This is connected to this paper here, but this paper not only has this discussion on multilinearity, it also has something that relates to sparse kernel-based approximations, because in sparse kernel-based approximations, you can think in the same way. You can think that, okay, your final answer is a function, but this function is essentially an identity operator. Now you can use identity operators in many directions, right? And then tensorize these differences and get this result. That is over there that I'm quoting from the paper again with Søren and Fabio. And this theorem that shows this convergence in Hilbert spaces covers the Matern case discussed before. Now, the interesting thing, and I'm not going to do this now, but in a few minutes when I get to multi-level regression, is that this type of sparse kernel-based approximations can also be tensorized in a sparse way with approximations in space, right? And therefore you can get convergence rates of the kind that I'm going to discuss when I get to multi-level regression with polynomials, okay? But I'm not going to do this now for the sake of time. Now, coming back to multi-index Monte Carlo and optimal sets, as I was telling you before, the assumptions on sort of algebraic rates that can be written as exponentials with respect to the beta yield optimal sets that are of this weighted TD or anisotropic TD. And these deltas to do the proper weighting relate to all the parameters that you saw before, essentially the weak convergence along direction I, the strong convergence along direction I, and the growth of the work along direction I. Okay, so all these things actually make for this tilting and provide you with the best choice of the subspace. Again, these are particular approximations. I say they do not hold in general, right? Only in some cases, but these cases are fairly common. Okay, so if you again go into this TD, well, you can show results in the finite dimensional case where you actually can get rid of this D dependence, right? This is you pay with a log factor here, but you can get rid of this dependence and put essentially more cases into this optimal type of convergence. You see the inequality is weaker now. And for the cases that actually do not fall into that, you still get a better, at least if you forget about the logarithm term, you get a better rate than compared to multi-level Monte Carlo, and of course with Monte Carlo, okay, because the D is not here. All right. So you say, okay, this is all fine, but what about the constants? I mean, this may look good with when you look at the exponents, but maybe the constants when you go and compute are completely different, right? And even though you gain in the exponents, the constants are much worse. That's a natural question. So here we have a 3D example, and we make sure that all the methods that we use actually track the error tolerance that we pose in a common way. And then we can compare, for example, the memory that sort of the multi-index structure is using. I mean, this is the memory of the largest problem that you have to solve in sort of alpha lattice versus the largest problem that you have to solve for the corresponding multi-level Monte Carlo or Monte Carlo, because they have the same bias problem. And then you see there's a huge disparity here, an advantage that gives you much more ability in the multi-index structure. And when you go to actually the convergence, or actually the convergence rate, right? Essentially the amount of work, in this case running time, versus the tolerance that you prescribe, the multi-index actually does much better. And this is just a comparison in 3D between multi-level Monte Carlo and multi-index Monte Carlo, both based on the same type of PD discretization, right? And you get an advantage from 10 to the minus 3 to 10 to the minus 2, and if you just do Monte Carlo, you get 10 to the minus 5, which is way worse. And if you go to 4D, well, then the situation is even more marked, right? You go 10 to the 2, 10 to the 4, and even 10 to the 6. Okay, so that's fine. So conclusions, multi-index Monte Carlo is a generalization of multi-level Monte Carlo, and provided that you have the right type of structure, you can exploit it and get better rates and saving a lot of computational effort in your problems. It does not relate to just time and space. You can introduce particles in your systems and other type of discretization parameters, right? So these are very flexible, and if you do the proper connection, you can also use this stuff in inverse problems. A quick example of a multi-index Monte Carlo and a stochastic particle system is given in this paper, multi-level multi-index Monte Carlo for Makin Vlasov, right? Recently accepted in statistics and computing. And essentially, what you're trying to model here is the evolution of a crowd. But it's interesting, right? Okay. So these kind of computations, right, where you try to track an interacting system here. These are particles that resemble people trying to escape from a given room here, and you try to compute observables out of this stochastic particle system when the number of particles is really large. Okay. So this is done with a MIMC lib. This is a multi-purpose library that is in GitHub, and it has different features. Haji Ali, who is in Oxford, is the main developer. There's a team not so large, but it's a workforce that is respectable to help him in that direction. Again, see. So advertisement, there's positions in KAUST and company, so you can read. I'm not going to say much. I don't need to read, but you can do it. Okay. Now, I thought you had enough time, so there's no more to add. And since it is filmed, you can always come back, so don't worry. Now I come back a little bit to the discussion that we had on the sparse kernel-based approximations. Now with the least squares approximation. So what is the problem here? You're trying to do a regression problem, essentially, random discrete regression. So essentially, you're trying to approximate in the best possible way a function by a given subspace here of polynomials v, right? In which sense, in L2, with respect to a measured mu, instead of sampling from mu, you're going to sample the function evaluations out of a density or measured nu that has sort of Radon-Nikodym rho. Essentially, you will evaluate this, and of course, you will, when you compute the discrete L2, you will take into account that you didn't sample from nu, but you didn't sample from mu, but you sample from mu. Yeah, you didn't sample from mu, but you sampled instead from nu. That's what I want to say. Sorry. Now, in a single level, then there has been work from Cohen and Migliorati that we used actually that says the following: that you can actually get away with this projection essentially, or make essentially the discrete L2 sufficiently close to the continuous L2 with only m to the log m samples, which is sort of optimal because less than m you cannot do it. Essentially, you need to determine m coefficients, so you cannot go beyond that. So unless you provide further structure, but in this case we are not, right? Then you have this sort of best approximation type of result connecting this L2 with respect to the best L infinity, and this holds with large probability. Okay, given the time, I'm not going to discuss too much how to construct this optimal distribution, but I will just go to the point. Essentially, in this context of trying to do a surrogate approximation from a noiseless evaluation of a function, you may have still the sort of what numerical analysis guys call discretization error. Okay, so this is not. Sometimes it is confused, right, as a stochastic error, but it's not, right? So this is something that is deterministic, namely you put the h discretization parameter, and you have many ways to estimate it a posteriori, a priori, and so forth. So, but what happens? Well, as we were discussing before, as you increase the accuracy in your sort of approximations for the PD, the cost per sample increases accordingly, right? I mean, say you are refining the mesh, you're getting better accuracy, but the cost per sample is going to get larger. So if you want to actually reduce the number of samples of maximal accuracy and instead try to introduce samples that are less accurate to improve the regression, well, then you have to do a sort of telescopic multi-level type of representation, right? This is what has been done on this multi-level weighted least squares polynomial approximation paper that is in archive. You can download it. So what is again the working assumption here? Like I said, we have a numerical method. This could come through finite elements, finite volumes, or whatever, that essentially gets more and more accurate as this refining parameter, you can think of a mesh size, is getting smaller. It converges with rate beta, yeah? And this doesn't come for free. You have to pay more because as you decrease the h, the work per sample is going to increase, right? Like h to the minus gamma, where gamma is a positive parameter. We also have some sort of approximability with respect to the subspaces VM, right? I mean, this function that we want to approximate depends on this parameter y now that you can think are these random inputs, and with respect to this is what we are going to use the polynomial approximation. So we need now a uniform sort of approximation property. Essentially, we say that for sufficiently small h, right, in a certain range, all these FHs, which are sort of approximations of the quantity of interest, right? We don't take expectation now, we just leave the quantity of interest as a function of the inputs, minus sort of the best approximation in this VM space is converging like m to the minus alpha, and again this is a property of VM and the dependence of this FH as a function of the y, say, like m to the minus alpha. Okay, so we need to have a rate as well. So we have two rates here that are coming into the game. One is beta for approximation in space, say, and the other is in the approximation of the polynomials uniformly on the h. And if you follow this line and you say, okay, what I'm going to do is a regression, and what I'm going to do, I consider the fact that I have inexact biased samples, right, that are affected by h. So I need to actually make this error small enough, right, like in the case of the bias for the Monte Carlo, and I also have to make the error of the projection sufficiently small, and this relates to the alpha. At the end of the day, I get for a fixed type of mesh where I sample my approximations this rate, right? If I want to get accuracy h, I have to pay essentially for the sum of these exponents here up to log terms. Okay, but forget the log terms for the moment. Now, if you do a decomposition in this way, again, you say, think of just one direction to make things simpler. I'm going to range L, right, from 1 to L capital. I'm going to find L capital in some way, again, to make the bias sufficiently small. And I'm going just to decompose my original F as a sum of differences, right, FL minus FL minus 1. Remember, this difference, again, is just difference between consecutive H approximations, right? And what I'm doing here is I'm projecting that difference in a given polynomial space here, and the whole thing is the following: that as L gets large, if you really have convergence with respect to H, right, the energy on this difference is becoming smaller and smaller. Therefore, we should need less and less polynomials actually to approximate it effectively. This is what is behind. Now, one presents this in this way, but actually you can do the whole construction in a multi-index setting as well for the best choice of the polynomial spaces and so forth. So if you do that, right, essentially if you take for the increasing accuracy less and less polynomials essentially in your subspace, you can balance this in the right way and show this result, essentially that you do not need to pay for the sum of these exponents. You just need to be controlled by the worst, which is the maximum quotient between work and accuracy on these directions. Okay, and this is the sort of type of result you can also get if you go with the reproducing kernel density that space that was given at the beginning, and I didn't discuss too much. Now this result holds in probability, right? So you control the error in this way with a probability larger than this, right? This is epsilon, and you have a result also that holds in L2. Okay, so these two alternatives provide the surrogate approximations for now the quantity f, say, of y, right? F now being not discretized and y being the inputs of your say, for example, random PE. Okay, so this is a numerical example. Again, the y is denoting random input. Here, it could be random or parametric, right? This is not much of a difference. But think that now you're trying to approximate the dependence of this quantity of interest, which is an average of the solution over the domain U, right, as a function of y. So you give me y, I need to represent this function that is real valued. Yeah? So if you have, for example, a dependence that is not so forgiving, in the sense that you just have algebraic decay here in the weights, you can still get, using this type of telescopic or sort of multi-level weighted projections, a rate that is algebraic with respect to the error in L2. All right. So, and this was just using a Fourier representation of the logarithm of the conductivity in this case, just to avoid, of course, negative values, as was the question when you asked Carita. Now, okay, so this I may have not made a comment on this point that was necessary, just not to confuse the two things. At the beginning, we were computing expectations, right? Either with Monte Carlo or with Multi-Index Monte Carlo. The number of samples was used for accuracy, right? They were controlling the statistical error, and they are used for accuracy. Without saying too much, when you go to the regression problem, actually, the samples are used for stability, okay, for the stable recovery, and the accuracy actually comes from the subspace, and in this case, the H that you use for the PDE. Now we go back to a problem where samples actually are used for accuracy, and in this case, it is the talk actually of Lorenzo, and I don't need to stop too much on that. Essentially, what Lorenzo told you is that if you have better additional smoothness with respect to the y's, right, instead of doing this expectation, say, with respect to using a quadrature that is Monte Carlo, you can use a quadrature based on sparse grids, right? And then the advantage that you can get from there is that you are not longer constrained by this rate told to the -2. Right? The told to the -2 essentially was to control the term 1 over square root of m, where m is the number of samples, and that's the way that the Monte Carlo converges in probability, right? If you change the integration rule, right, and you use something deterministic and your function is really in the correct space, you can get something that is much more beneficial and goes much faster in terms of the work. Okay? That's motivation. And of course, you need assumptions in this case as well that they relate to Kirchhoff's talks on the holomorphic dependence, because now you have a linear PDE and the coefficient is expressed in terms of an analytic function. You can show the results of the corresponding convergence in the sort of finite dimensional input case, or you can also go into infinite dimensional as well. Now, if you make the practical comparison, right, of the different methods, the multi-index actually does better than the MultiLevel version of the stochastic collocation, and also, of course, the Multi-Index Monte Carlo, which in this case is just converging, even though with the optimal rate, but it's not exploiting this available rate regularity, right? So, again, MultiLevel Monte Carlo in this problem is converging optimally, but it's not near close to what you actually can extract from the regularity available in the problem. Okay, you can also do the infinite dimensional case. How much time do I have?
20 minutes.
Okay, thank you. With questions, without questions? With or without questions? Without questions.
Without.
Yeah. Yeah. Okay. Good. So I can cut down a little bit. Thank you.
Let's calm down a little bit.
Yeah. So, yeah, I'm mostly inviting questions. That's what I'm doing. So, log uniform field with parametric regularity. This example that was essentially treated in a follow-up paper, again with Lorenzo, Fabio, and Abdo, was motivated by essentially the need to understand how this method will converge now in an infinite dimensional setting. And again, we wanted to produce a result that only depends on the regularity and not really on the number of variables that are input, because these are just infinite in all the cases. So yeah, we were able to show a theorem, which is this, that combines the convergence rate of the finite element and the summability of the coefficients in the input coefficient, and then get rates that essentially say that if you have enough regularity in this case, nu is written here because the field that we were working with was trying to resemble a Matern type of dependence. So as nu gets larger, the input field is getting smoother, right? So what happens here essentially is that as nu gets larger, you recover the convergence rate of a deterministic problem, discretized with a given finite elements method, correct? And then this is a great result in the sense that even though you have infinitely many random variables to deal with, you recover, if you have enough smoothness, the rate of a deterministic problem, right, in 1D up to log terms. Okay, but again, this doesn't happen in all the cases. You need to have the right regularity. The only case that I'm making here for is that if this regularity is available and you know that it exists, why not using it, right? It can give you more savings. Okay, so now these techniques can be used also in the context of multi-level for inverse problems. We have some work done on data simulation and filtering, some smoothing, and the regression I just touched, right? And again, in connection to you can think of this as part of an inverse problem, or actually as a part of surrogate type of reconstruction, right? And in the surrogate, the connection that I made was between this work and the other work with the reproducing spaces. Now, let me give one word about optimal design of experiments. Essentially, in the optimal design of experiments, one of the formulations can be written as the maximization of the expected information gain, which is essentially the Kullback-Leiber discrepancy between the posterior density and the prior density. When you try to compute this functional, I mean it's just a functional, and you get into a nested expectation. Okay, so and this nested expectation cannot be decoupled as you would do with a sort of normal Monte Carlo computation and just make it a single loop. It's really a double loop. So if you don't exploit the structure, you get, you know, the square of the rate of Monte Carlo, which is pretty bad. Okay, so in order to get rid of or at least to improve this nasty dependence on this double loop, essentially, we need to understand that with respect to the number of available experiments, you know, the posterior essentially concentrates. Of course, provided that you have identifiability in your parameters with respect to the data, right? So if you do that, actually, there's a nice trick based on the Laplace approximation that essentially allows you to do an important sampling technique in this problem that allows you to reduce substantially the work that you need to invest to solve for this quantity. Okay, so that's really what is key, and of course you then compute combining these measure changes, right, with discretization in different levels of a hierarchy, right? That could be multi-level or multi-index. So this can, for example, be used in impedance tomography, where you just send currents to try to understand what is the corresponding, for instance, orientations of angles inside of a composite material, for instance. This is a non-destructive type of test, so it's of high use, of course. You don't have to break anything. So you have, for example, in this case, 2 plies, right? And you pass, you inject current in some of these electrodes, and you take them out, and that's your control parameter somehow. And what you will observe are the voltages, right, in the different electrodes. And from this, you try to gain most of the, as much as possible information on these orientations, which are here, the alpha 1s and alpha 2, the parameters that you want to infer. So what can be parameters in this case? Well, the shift between the different electrodes, the size of the electrodes, and so forth. And you can have then the corresponding streamlines, just to understand what is going on, and we don't let any currents go out from this slab, right? Everything is happening in this context only. And then you can still have nice information gain. So it really pays to actually put these things in the right way, because if you put them in the right way, you get this increase in the expected information gain. And if you compare sort of the posteriors that you get using that point up there versus something that is here, that is concentrated with respect to this one. In this type of example, which is also interesting, I think, you have the ability to say, for example, which are the currents that you're going to inject in I3, and this is the same that you're going to be taking out in this other point, I4, right? The other two are fixed. And then you say, okay, maybe I'm trying to learn the angles on the red part and the blue part. Will that make a big difference if I inject more or less, actually? Well, it does actually, because if you inject it in the way above, for example, which you're pulling out current on the left up, down, say, and injecting on the right down, essentially most of these sort of rays, if you wish, will go through the lower part, right? So essentially this will tell you a lot of information about the blue part. I think the blue was in the bottom, yes, the blue part, but it will not tell you much about the red part. So essentially what you will have is like almost a non-informative posterior with respect to the first parameter, whereas in the second one, when you send the rays essentially through the whole domain in a more uniform way, you learn about the two. And you see this in the posteriors. The red will be the sort of non-optimized one, and the blue will be the optimized one. You really concentrate both parameters, whereas in the other one, you don't learn much about the red part, and you see this sort of still flat prior with respect to one of the parameters. That's essentially what happens. This is a zoom, so there's not much to add on that. So this is just a little bit of an advertisement now. So what happens in these problems with geosciences sometimes is that you have coefficients A that relate, for example, if you think of 1D, to a covariance that has this type of dependence, right? That has a non-differentiable point at 0. And this essentially gives a regularity for the corresponding realizations of the field, which is almost C1/2, right? And if you try to go and do the usual finite element estimation in this context, well, it's not really it's not really used for this situation. So to address this issue, we discuss a little bit the situation in this paper and produces some estimates in terms of the coefficient that tells you essentially how the error is accumulating in a quantity of interest computed out of the solution of U. That's essentially what is going on there. A little bit about the Monte Carlo, and I think I'm done. Okay, so conclusions again. I tried to make the case for the use of available regularity using multi-level and multi-index methods. One of the things that I focused on was the use of multi-level weighted regression to produce surrogates, right? And in this similar sort of competitive line, we have this other type of approximation based on radial basis functions. Okay, that could be also tensorized to get similar type of results as in the multi-level regression. But these are other families for approximation. Okay, thank you.
Questions?
So I've been struggling now for about 4 weeks to try and understand the relationship. So in one type of method, I'm going to be very naive, one type of method you do use Monte Carlo and you have means and variances.
Correct.
But in the what you call the deterministic method, you just have biases.
Correct.
No. So what you're telling me is that you can use the MultiLevel simulation techniques in both, in the Monte Carlo
Yes.
thing and in the where you
Correct.
just have biases.
Correct.
But they're slightly, subtly different. One you have more error bounds, and the other you can use variance. Is that roughly a rough
They are both
summary?
error bounds. I mean, the error bounds work in probability. So from the numerical analysis point of view, Monte Carlo is a discretization of an integral as much as trapezoidal is a discretization of an integral. The corresponding error for each of them comes from the nature of each method, but they do not stop being quadratures, each of them.
Thank you very much.
Okay? Thank you.
Other questions?
This must be a tough one.
Are you allowed to ask a question?
I don't know. As you wish.
Okay, you go ahead.
Yeah, it might be beneficial. In the multi-level regression, you didn't say how you chose the multi-index set you want to regress in.
This is why I said that it was written in a multi-level setting because it's easier to understand. But really what is behind the choice of the polynomial spaces and everything is a multi-index construction, right?
Yes.
Where you actually try to understand the level sets of the different things involved, and then based on that, you decide whether a TD, an isotropic TD, is the right structure or not for the subspaces that you're going to use.
Okay.
Okay? In the paper, it is done so that
Okay.
the TD actually ends up being the right thing to do. But
Okay.
by no means I claim that this is a more general situation.
So it's the
In
usual.
particular problems you may have.
So either a priori you fit the anisotropic
Yes.
rates or adaptive, and you
Yeah,
have
but
lineage
there are cases where a priori you know that
Yes,
TD
yes,
is not
of course.
optimal.
Yeah.
And then you should use that structure and not TD.
Okay.
We are not married with TD.
Other questions? Okay, I think we can thank Raul again.
Thank you again.